Now another kind of filter is a Chebyshev filter. This filter has many advantages or disadvantages over the Butterworth filter, but the one of the advantages is it has greater suppression or greater attenuation of the frequencies in the range of the frequencies that it has to stop, meaning that it will suppress those frequencies to a greater extent than a Butterworth filter. But this filter comes with its own disadvantages, that it has a ripple in its passband, meaning the frequency response of this filter is somewhat irregular in its passband. I'll show you how. So here I am using a cutoff frequency of 250 Hz, and I've used the Chebyshev function of the SciPy library, and I've given it as a low pass filter. Now I'll run this part of the code and we see that this is the response of this filter. We see that in its passband, which is the frequencies which are less than the 250 Hz, we see that this, if I zoom in on this frequency response is not as flat as the Butterworth response we just saw above. This has a ripple, meaning it has somewhat irregularities in its passband which may cause distortion in our original signal. But then there's an advantage of this, that it has a higher attenuation in its in the band that it has to stop. Okay, so the next type is high pass filter. Using the same Chebyshev function of the SciPy library, I am plotting the response of a high pass Chebyshev filter. I'll run this part of the code and we can see that it allows the frequencies in the higher side of the cutoff frequency to pass and attenuates the lower frequencies. But again, we see that there's a problem here, that this curve is not flat. It has some ripple, it has some variations in the response, and this will cause some distortion in our original signal. The next is the bandpass filter. Very similar thing to the bandpass filter of the Butterworth response. Here again, the range of frequencies will be allowed to pass and rest of the frequencies will be rejected. But again, when I run, we can see that if I zoom in its passband, here the response is not flat, meaning it will cause the distortion in our original signal. Rest of the functioning is very similar to the Butterworth filter. The last type is the bandpass filter. Bandpass filter is exactly opposite of the bandstop filter. It allows the frequencies outside of this band to pass and attenuates the frequencies in between this band of frequencies that we mentioned. Here I mentioned the frequencies from 250 Hz to 350 Hz, and when I run this code, we can see that it attenuates the frequencies in this band, which was 250 to 350, and lets the frequencies outside of this band to pass through. But then we can also see that there are ripples, there's distortion in its passband, which means that it might distort our original signal as well when we pass the signal through this. So that was all for the filters. One last topic that I like to touch on is the short time Fourier transform. I like to demonstrate this using a Python code in which I read a wave file, which is an audio file. I'll plot its FFT, the Fourier transform, and then I'll show you the short time Fourier transform of it using this function STFT. Now what short time Fourier transform does, it shows us presence of certain frequencies at a given period of time, which the Fourier transform itself does not. Now when I run this code, we see that this is the plot of the wave file, of the audio file that I chose. We can see that it contains these are the small words that were there in the spoken in that audio file, and then this is the Fourier transform of that audio file, in which we can see there are certain frequencies that are present more than the other frequencies. Now when I plot the short time Fourier transform of this wave file, we get a plot which is something like this. Alright, so on the y-axis we have frequencies, on the x-axis we have the time, which in this case was 40 seconds, which was the length of the audio file. Now we see that there are different intensities on this, which are plotted on this graph. Now what do this signify? This intensity of a color on the plot signifies what is the magnitude of that frequency present at that particular period of time. So we see that from that in the starting, maybe say the frequencies in the range of say under 2000 or under 3000 are highlighted more than the frequencies in the higher side, which is also result in the overall this graph. We see that, so since our human frequency speech frequency is up to almost 3300 hertz, we see that the and this plot has very bright spots under this 300 3000 hertz range, and then there are very light spots above this, which shows the presence of certain noise or other frequencies in the signal. But my main motive to show you this plot was that the advantage of short time Fourier transform over a normal Fourier transform is that we can see the presence of frequencies at a given point of time, which is not possible in a normal Fourier transform. So that concludes our signal processing workshop. I hope you guys learned a lot from this, and I thank you for watching this.